Have you ever looked at a graph, one with all those twists and turns, and wondered, where's the very highest point or the absolute lowest? Well, today, we're basically going to go on a mathematical hike to find exactly that. We're going to pinpoint the maximum and minimum values of any function. So let's dive in. See, if you have a picture of the graph, it's pretty easy to just point and say, there it is. But what if you only have the equation? That's a whole other ballgame. How do we find that highest peak or that deepest valley using just the tools of calculus? That's the big question we're going to answer today. All right, so in calculus, we call these peaks and valleys extrema. But here's the interesting thing. There are actually two types. You've got your local extrema, which is kind of like the king of the hill. It's the highest point in its immediate little neighborhood. But then you have the absolute extremum. That's the king of the world, the single highest or lowest point across the entire function. So, how in the world do we find these kings? We can't just check every single point on the graph. That would take forever. Instead, we hunt for special locations, places where the function's slope gives us a big clue. The whole idea is that a peak or valley can only exist at these special spots, and we call them critical points. So what exactly is a critical point? Well, it's a point where the slope of the curve does one of two things. First, the slope could be 0. Just picture it. You're climbing a smooth hill, and right at the very top, for just a split second, the ground is perfectly flat. That's a slope of 0. The other option? The slope is undefined. This happens at sharp, pointy corners. These two places, flat spots and sharp corners, are the only places we need to look for a maximum or minimum. And that leads us to our game plan, a really simple but super powerful 3-step method that works every time. Step 1, you find the derivative of the function. Step 2, you use that derivative to hunt down all the critical points. And step 3, you test those points to figure out if they're a max, a min, or maybe neither. Let's put it into practice. We're going to start with a classic, a really simple downward opening parabola. This is the perfect function to take our 3-step method out for a test drive. Okay, so our function is f of x equals negative x squared plus 4x. Now, you might remember from algebra that the negative in front of the x squared makes the graph an upside-down U-shake. So right away, we should be expecting to find one single peak, a maximum value. Let's run through our method. Step 1, find the derivative. Easy enough. The derivative, f prime of x, is negative 2x plus 4. Step 2, find the critical points. We just set that derivative equal to 0 and solve for x. So negative 2x plus 4 equals 0, a little bit of algebra, and we get x equals 2. That's our only critical point. Step 3, we evaluate. We take that x value of 2 and plug it back into our original function to see how high the peak is. And we get 4. And boom, there it is. The process totally confirms what we thought would happen. This function has a local maximum value of 4, and it happens right at x equals 2. See? Simple, clean, and really effective. All right, that was a pretty good warm-up. Now let's level up and tackle something a bit more complex, a rational function. This one's got a few more twists and turns, and to find its derivative, we're going to need a special tool called the quotient rule. So here's our new function, f of x equals x divided by the quantity x squared plus 1. This curve is sometimes called the serpent because it has this really cool, winding, snake-like shape. It goes up, it comes down, and then it levels out. So this time, we should probably expect to find both a local max and a local min. Okay, so step 1, the derivative. We apply the quotient rule, and after a bit of work, we get this fraction here. Now for step 2, finding those critical points. Remember, a fraction is equal to 0 only when its numerator, the top part, is 0. So we just set the numerator 1 minus x squared equal to 0. That gives us two solutions, x equals 1 and x equals negative 1. Now hang on, this is a super important point and a really common mistake. Remember how critical points can also happen where the derivative is undefined? For a fraction, that means we have to check if the denominator, the bottom part, can ever be 0. But in our case, the denominator is x squared plus 1, all squared. And since x squared is always positive or 0, x squared plus 1 can never be 0. So, phew, no undefined points to worry about this time around. So, after we test our two critical points, here are the results. At x equals 1, we find a local maximum with a value of 1/2, and over at x equals negative 1, we find our valley, a local minimum with a value of negative 1/2. Okay, for our last example, we're going to look at a totally different kind of beast. What happens when your peak or valley isn't a nice smooth curve, but a sharp, pointy corner? This is where that other type of critical point finally comes into play. Let's take a look at the absolute value function. F of x equals the absolute value of x. We all know this graph, right? It's that perfect V shape with a super sharp point sitting right at the origin. Now, to find the derivative here, you kind of have to think of this function as two separate lines stuck together. On the right side of 0, the function is just y equals x, so its slope is always 1. And on the left side of 0, the function is y equals negative x, so its slope is always negative 1. And that brings us to the million-dollar question. We know the slope just to the left, and we know the slope just to the right. But what is the slope exactly at that sharp point, right at x equals 0? And the answer is, the derivative is undefined. Think about it. Since the slope coming from the left, negative 1, doesn't match the slope coming from the right, positive 1, the derivative just doesn't exist at that one single point. You can't draw a single clear tangent line. And since the derivative is undefined there, that means, by definition, x equals 0 is a critical point. So here's the big takeaway. Even though the slope wasn't 0, we still found our extremum. We can see from the function itself that f of 0 is 0. And for any other number you plug in, the result is positive. So that means x equals 0 has to be the location of the absolute minimum value. Okay, we've climbed 3 pretty different mathematical mountains today. Before we wrap this up, let's stop and review the key tools we just added to our hiking pack. So here's your toolkit. First, always remember the 2 types of extrema, the local kings of the hill and the absolute kings of the world. Second, to find them, you always hunt for critical points. And where are they? They're where the derivative is 0, your smooth tops, or where it's undefined, your sharp corners. And finally, your go-to plan of attack is always that 3-step method: derivative, then critical points, then test. You now have the fundamental map and all the essential tools you need to explore the landscape of pretty much any function. So the only question left is, which peaks and valleys are you going to discover next?